Today we're going to finish up our discussion about binary trees by doing a little bit of mathematical analysis of binary trees in order to justify my claims that I made earlier about the operations of a binary tree having logarithmic time complexity. For this, we use a new definition that the height of a tree is the number of edges on the longest path from the root to a leaf. This may be inconsistent with other sources, such as the optional textbook. I don't know. Oh, man. That completely discombobulated me. Oh, yeah. Some sources will count nodes instead of edges, which will get us an answer that is off by 1 in terms of the counting method that we're using for this course. So be cautious of this if you're ever asked to state the height of a tree. But luckily, in big O notation, that sort of wipes away the difference of at most 1. It'll be log n either way. As an example, in this tree, I see 2 longest paths from root to leaf, starting from 18 going like this. It's the longest path from a root to a leaf. And this one is just as long as the one I saw before. I guess there's another one that goes to 9. Cool. And the path from 18 to 36 is not the longest path because, of course, others have 1 node below that, and it would be 1 longer. So to find the height, you just count the edges. 1, 2, 3. And thus, the height of the above tree is 3. It's a pretty simple concept, but make sure you know it because all the stuff about time complexity for these will depend on the height. Yeah?
So you said okay with any tree is log n?
Yeah, there are exceptions, and we will get into those, but in general, it's usually log n. And we'll see when it isn't log n. So as a sort of warm-up for finding the time complexity in terms of n, the number of nodes in the tree, we'll take a look at the time complexity of its operations in terms of h, the height of the tree. So using big O notation, and in terms of the height h, think about what the worst case time complexity of insert, search, and delete are. We'll go through them in order, and they're going to all have sort of similar answers. So think about what will cause the insert operation to take as long as possible. Clearly, this worst case isn't if we're inserting something between 12 and 18, because then it only has to traverse 1 edge and create another. Clearly, it isn't inserting a node after 36 because it would only have to traverse 2 edges. The worst case for insert must be if we're inserting a new node on the longest path from a root to a leaf. Something like this. Remember that a typical implementation of an insert method would involve some sort of loop, like while the applicable child does not null, follow that path until you get a failed search and put the node there. So the conditions under which insert will take the longest time is if you're inserting a node at the very bottom, like this. search and delete operate or have almost the exact same worst case. In fact, I probably should have gone through them first because it's simpler. The worst case for search and delete is if the node you're looking for, either to search for or to delete, is on the bottom of the tree. Since we start from the root at all times, that'll take the longest possible path to get to that node. I suppose the true worst case for delete is if the node doesn't exist, but if it did, it would be on the bottom layer. Like if we were told to delete 20, we would traverse one edge, two edges, three edges, and then attempt to go through a fourth, but that would fail. So all of these operations have worst cases in which we need to traverse the most edges possible. And that most edges possible is the height of the tree. The worst case scenarios for all of these is when you have to traverse the entire height of the tree. And the slide had a little extra condition. Maybe we could make the delete method faster if we assume that the delete method receives a pointer to the node to be deleted. So you don't have to search for it. Like, if I have to delete 25, my delete method just has a parameter node to be deleted, and I don't have to search for it. Cool. That definitely improves the average case, because most of the time the pointer will make it so you can delete something in constant time. But what if we were told to delete 18 here? We would have to find its successor in order to swap that node with its successor and then delete the node from the new position. You know how it is. And to do that, we would have to, guess what? Traverse the entire height of the tree. Wah, wah. So if we're given a pointer to the node to be deleted, that will improve the runtime of the algorithm a lot of the time, some of the time. But you can't get around the need to search for that node's successor, and that search might involve traversing the entire height of the tree. So while the average case improves, the worst case time complexity of delete is still O of H. So that's pretty cool. All of these operations have time complexity big O of H. But H isn't really that meaningful, honestly. Like, if I tell you I have a tree of height 4, am I talking about something like this? Or am I talking about something that I probably won't finish the drawing of because it's pretty tedious? Actually, this is a tree of height 4. It's fine. When considering data structures and also algorithms, we almost always want to compute time complexity in terms of the number of things in the data structure, or the size of the data structure, or number of things in the data structure that's passed to the algorithm. So saying that it's O of H hides a bunch of information. So in order to express these operations' time complexities in terms of n, we need to express h in terms of n. So in terms of h, what is the maximum possible number of nodes in the tree? Sort of the worst case for this? Well, let's make a table and see if we find a pattern. We're not going to go for that long. A tree with no nodes or just one node, we say has height 0. Indeed, the longest path from the root node to a leaf is 0 because our root node is also technically a leaf. Since we can't insert any more nodes without increasing the height, clearly the maximum n, when h is equal to 0, is 1. Now let's check out a tree of height 1. I've added 2 nodes. Because we're concerned with binary trees, I've completely saturated that level of the tree. I can't add any more without increasing the height. And let's see, 1, 2, 3. Maximum n is 3. Now I'm going to add another level and completely fill it up. Now, with height 2, I can add quite a few nodes this time. Looks like 7. It increases in a way that's somehow bounded by the number of nodes that are already in the tree. And let's go for one more level. That was a lot. I basically just duplicated all the effort that I already put in. Indeed, I almost doubled. This is looking pretty close to 2 to the n. I guess if you added 1 to h and then subtracted 1 from the result, you'd get 2 to the n, something like that. No, that's how you would get the height from 2 to the n. I'll just write it down. So that's my guess based on the numbers that we got. It seems like given a height h, you can get the maximum number of nodes in the tree by computing 2 to the power of h plus 1 minus 1. And of course, that's the worst case. N is at most 2 to the power of h plus 1 minus 1. As demonstrated earlier, you can still have a tree with the same height, but significantly fewer nodes. The tree that we just drew is called a perfect binary tree. The thing that makes it so perfect is that every single level is completely filled up. There are no gaps. And that will sort of be the scenario that we look at because it provides an upper bound on n. Sort of a worst case. And then here is, I think, pretty much the exact same as the formula that I wrote down on a previous slide. We actually have a summation identity for exponential functions. You don't need to know this. It appears on an assignment, but it will be given to you on that assignment. Summing up 2 to the j for j from 0 to h, you get 2 to the power of h plus 1 minus 1. So now we have a way to get n from h, which means that we're so close to being able to express n in terms of h. No, h in terms of n. Replace h by some expression of n. So, using this trusty formula and doing a little bit of algebra, you would have to add 1 to both sides to cancel out that minus 1, and then do a logarithm of both sides to cancel out that 2 to the power of. And you'd end up with, not that, h equal to log base 2 of n plus 1 minus 1. This is in big O of log n. And of course, because big O notation isn't just this thing made up to torture second-year students, but it's an actual tool used to simplify things in discussions of computational complexity. This log base 2 of n plus 1 minus 1 thing simplifies to just log n. We don't care about the details. It's logarithmic. This makes it so the worst case time complexities of insert, search, and delete, which we previously found to be big O of h, are all big O of log n. Not as good as a hash table, but better than a sorted linked list. Plus, we can traverse the data structure. Yay! Now, this slide has something kind of weird in it, something that might seem like a contradiction. We see that in the best case, the worst case time complexities are like that. Which is it? Pick a side. Is it the best or the worst? These are discussing sort of different, different scenarios? No. I don't know how to generalize this. I'll just explain it directly. The best refers to the data structure, and the worst case refers to the time complexity of the algorithm. The best case data structure is this perfect binary tree. Every level is completely filled up, and we've minimized the height for the maximum possible n. So this is the best case of the data structure, which makes it so the worst case of the algorithm is log n. So what's the worst case of the data structure? Well, something that's going to basically motivate the next week or so of the course, because binary search trees are pretty sweet if you insert items in just the right order. If you don't, you might end up with this. The height h is not always logarithmically related to the number of nodes. Sometimes, if you really screw up, h will be equal to n minus 1, which is O of n. We get that because there's an edge connecting every pair, or every 2 consecutive vertices. And there just isn't an edge corresponding to the last one, n minus 1. So this is pretty terrible. If your binary search tree is managed badly, then the thing just becomes a linked list. The last couple lectures were a complete waste of time. And so the next big chunk of the course will discuss how to fix this. Binary trees have advantages worth keeping around. You can do binary search on a linked data structure. Sweet. But we want to avoid stuff like this. Sort of related before we move on, this is something that I think has happened in the real world. Nowadays, companies and the programmers within them are a lot smarter than to just use binary trees. But it is sort of a known method of attack to send data to some enemy, like a website that you want to crash, in an order that'll make their data structures take on their worst case. So if security is of any concern to you, which it should be, the lessons in this course will help you fortify the systems you create. That's the end of this slide deck. I'm going to keep talking, though. I think this is the slide deck for today, and I'm going to move on to next Monday. I'm hoping that eventually we'll be able to get one full day ahead, because that'll make it so the cutoff for studying for quizzes on Thursdays will become Tuesday instead of Wednesday. You'll get an entire day extra of studying time, which in a condensed course really matters because that's doubling your study time. So let's get on with it. So recall that binary trees work really well as long as the data happens to be arranged nicely. But if it doesn't, it just degenerates into the thing we were trying to improve in the first place. And since we're looking at worst case in general, this makes the worst case time complexities of all of the binary search tree operations O of n. In practical terms, pretty bad. So if we want to keep O of log n time complexity in all cases, we need to look into ways to force the tree to actually look like a tree and not a stick. The name for what we're going to look at is balanced search trees. They are like binary search trees, but they have additional restrictions or complications to the structure and their algorithms in order to prevent this worst case behavior. We're going to look at 2-3 trees right away. And then there are some other trees that we might look at, some that we won't look at. 2-3 trees change up the structure of a binary tree. AVL trees have the same structure, but have restrictions on how to insert stuff. And then red-black trees and B trees, I'm nowhere near as familiar with. But I know that B trees are used pretty extensively in the real world for databases. I mentioned earlier that the ability to do binary search on a linked data structure, such as a binary tree, is what made it even possible to search for things like videos on YouTube or users on a social network. I was being mostly truthful. Like, the ability to do fast lookups does make that possible, but they sure don't use binary trees because they're bad. So let's take a look at 2-3 trees. We're going to sort of skip straight to the recursive definition of these guys. A 2-3 tree of height 0 is a single node. Sounds good so far. a 2-3 tree of height h strictly greater than 0, so like 1 or more, can take on one of the following two shapes. It can be a root node with two children, each of which is the root of a 2-3 tree of height h minus 1. Also familiar, if we just stopped here, then we would have binary search trees. The definition is identical so far. But it can also be a root node with three children, each of which is a 2-3 tree of height h minus 1. So they're not binary anymore. We've lost the binary part of binary search tree because 2-3 trees can have nodes with three children in them. And this probably, like most likely, isn't clear right now, but our definition actually forces 2-3 trees to be balanced. No matter how exactly you insert stuff into it, it's always going to have height is in big O of log n. I almost certainly won't be able to explain why in the confines of this class, so I think I'll just leave that as a bit of a cliffhanger. How exactly does this cause the entire tree to be balanced? I don't know. Find out next time, and good luck on the assignment.